Let's get some practice computing the coefficient of performance for a refrigeration cycle, one for which we are given the PV diagram. So let's say that we have this cycle composed of three different processes, and we're told to ignore kinetic and potential effects. What that means specifically is that delta KE and delta PE equals 0 for each step, namely each process in the cycle, in addition to being true for the entire cycle. So for a refrigeration cycle, the first thing we ought to do is just sketch out how the cycle should work. So we have heat transfer from a cold reservoir to the system, heat transfer from the system out to a hot reservoir, and work is done on the system. Keep in mind something like a refrigerator where you have to plug it in, so you need work to go into your system in order to keep the cold side cold and the hot side hot. Okay, we're also given information about various aspects of each process. So in one case, we're told that Q12 equals 0 kilojoules. That just means there's no heat transfer in process 1 to 2. And we're told over here that the change in internal energy in process 2 to 3 is minus 800 kilojoules. It may seem odd that we're given these random bits of information. In order to solve this problem completely, what we're going to have to do is go through and figure out the other pieces of the puzzle. So we want Q values for all three processes, delta U values for all three processes, and works for all three processes. You'll see how the pieces fit together momentarily. So our first step, logically, would be to start with process 1 to 2, and let's just go ahead and compute the work from 1 to 2, which we can do geometrically. It's nice. I don't know if you noticed, this is a triangle. We can handle that one without any integration. So the first thing to notice is that going from state 1 to state 2 is going left on a PV plot. That means that it has to be a negative value of work. And then we just add up the areas. So we need, remember, the area of the triangle and the area of the rectangle between the base of the triangle and P equals 0. So this first term here, 1/2 base times height. It's kind of sloppy, but you can see that the base of this is just the difference between 4 and 1 cubic meter for the volume difference. 500 kilopascals minus 200 kilopascals is the height of the triangle, and the 1/2 is out front for the 1/2 base times height formula for the area of a triangle. So that corresponds to this bit right here. Our second term over here is, of course, the area of the rectangle underneath the triangle there, and that's just a base times a height, so it corresponds to this region down here. Alright, so those two regions added together with a minus sign out front give us work 1, 2, and we can go through and simplify this a little bit, and we get that it's minus the quantity, 450 kilojoules, plus 600 kilojoules, those are the two areas, and that tells us that work 1, 2 equals minus 1050 kilojoules. As we go through and compute these quantities, I'm going to write them over on the left side of the screen so that we don't forget what they are, so I'll put this one by process 1 to 2 on the PV plot. Okay, so now we know the work. If we use conservation of energy, generally speaking, we would know for this process that delta KE12 plus delta PE12 plus delta U12 must equal Q12 minus W12. I won't say that in words every time, but that's conservation of energy for process 1 to 2. Well, remember, we can ignore kinetic and potential effects, so this simplifies to the change in internal energy equals Q minus W. We're told, over on the left, that Q12 is 0 kilojoules, so there is no heat transfer. That tells us that delta U12 equals minus W12, so that means that delta U12 must be positive 1050 kilojoules. Now you may ask, why do we care about the internal energy all of a sudden? We weren't asked to calculate that. Well, remember, in computing the coefficient of performance, we actually need to separate out the heat transfer going into the system and the heat transfer going out of the system. To do that effectively in this particular problem, we'll need to consider the internal energy changes. You'll see in a minute. Okay, so we'll write delta U12 over on the left side of the screen, and we've got that. Next step. Well, the work is easy for process 2 to 3. It's 0 because it's a vertical line on a PV plot. You should be pretty comfortable with that now. I'm going to write that over on the PV plot so we don't forget. Now let's consider the change in internal energy for U23, which we are given as minus 800 kilojoules. Once again, we can use energy balance, ignoring kinetic and potential effects, to say this, and we can go through and plug in our value of W23, which after all is 0. That tells us that the change in internal energy for process 2-3 is equal to the heat transfer. They're both minus 800 kilojoules, so Q23 must be negative 800 kilojoules. We'll record that. The next step, process 3 to 1. Well, the work, we already know, it's just going to be this area, and W31 is positive 600 kilojoules. Again, we're going to the right on a PV plot. That should remind you that the work has to be positive when we already computed that area as part of our process 1 to 2 work. So W31 is 600 kilojoules. We now have the total work for our cycle. What about delta U31? We use energy conservation, but now we're actually a little stuck. We aren't given any information about process 3 to 1 aside from its work, but the nice thing is we know what the sum of all the changes in internal energy must be. Delta U total has to be 0 because this is a cycle, and this is really the power of cycles, is that if you can figure out, for instance, 2 out of 3 process changes, such as the changes in internal energy for process 1, 2, and 2, 3, you can get the change in internal energy for process 3 to 1 because you know that you have to end up back at the place you started. So it's true that the sum of all the changes in internal energy for the 3 processes is 0. We'll move that up and use that in a second. That means that if we're solving for delta U31, we can plug in our values for delta U12 and delta U23 that we've already computed. So we do that, and we get out that delta U31 is minus 250 kilojoules. We may not need to record that value for much later because we're going to use it immediately, but I'll go ahead and write it on the left side. The way that we're going to use it, of course, is with energy conservation for process 3.1. So we know that delta U31 must equal Q minus W. We know the value of delta U31, and we can put in the value of W31 to solve for Q31. So we get that Q31 is 350 kilojoules positive. That we'll record over on the left. So we have all of our work values for the 3 processes, all of our heat transfers for the 3 processes. What's the next step? Well, in order to actually compute the coefficient of performance, we first need to think about what represents Q in and what represents Q out in this cycle. Well, in this particular cycle, Q in corresponds to positive values, right? Because generally speaking, according to the conservation of energy law, it would be the case that delta E total equals Q minus W. If you have a positive Q, that means that you're adding energy to your system through heat transfer. That corresponds to Q in. Energy is being added to your system. Well, if we look at the heat transfer values in our case, we have 1 0 that we don't care about, 1 negative value that we don't care about. The only positive value we have is Q31, which is positive 350 kilojoules. That becomes our value of Q in. Just to be absolutely clear, if we needed to know about Q out, which we do not for this problem, Q out would be positive 800 kilojoules because, again, once you put the subscript on Q, whether it's Q in or Q out for a cycle, you assume that the value that you're describing is positive. The word out tells you that it's negative with respect to the system if you use the conservation of energy. It's a confusing notational issue, better than having absolute values everywhere. So now that we know that, we can also go through and compute the total work in order to compute the coefficient of performance. So the total work is just the sum of the 3 different work values that we have, and here we do retain the signs to make sure that we get the total work right. We'll take its absolute value at the end if we need to. So moving this up, the total work is minus 1050 kilojoules plus 0 plus 600 kilojoules. That gives us a negative 450 kilojoules. So now if we describe W cycle, the subscript cycle tells us that we want a positive value for this associated with the total work done by the cycle. That means that W cycle equals the absolute value of W tot, which is 450 kilojoules positive. Now we have the 2 ingredients that we need to compute this coefficient of performance. We have Q in and W cycle. If you consult your lecture notes for the coefficient of performance for refrigeration, you'll see that it's a variable beta defined to be Q in divided by W cycle, and in this case we just plug in those 2 positive numbers, 350 divided by 450, both in kilojoules, and that gives us a value of beta of 0.78. Now you may see that value and think, well, that's a pretty good efficiency. Here you have to be a bit careful. The coefficient of performance for refrigeration can actually exceed 1, meaning that unless we compare this to another cycle, we don't really know how well we've done. This is actually a little bit on the low side. A word of warning when distinguishing between power cycles, refrigeration cycles, and heat pump cycles, the coefficients of performance or efficiencies in the case of a power cycle are different from one another. It's very easy to confuse them, so you want to make sure that you are using the correct expression for each different cycle. If you use the wrong one, you're misrepresenting the efficiency or the usefulness of your cycle.